share the screen, but now I need something else. Also, just have a little patience. Okay, do you have that whiteboard in front of your eyes?
Yes.
Yes.
Okay, let's start. So, if you remember, I promised you at the seminar that I will bring this evening an exercise where unfortunately we can't apply the Sylvester theorem nor the method with the eigenvalues. Do you remember? I told you that today we'll do this kind of exercise. Okay, so you will see that is not too difficult. Actually, it's nice. So the first exercise, the request of the first exercise is to determine the local extrema of the following function of f of x and y, where f of x and y is 4 times x times y minus x power 4 minus y power 4. Okay, let's start. We'll do it as we learned at the course and at the seminar. First of all, the stationary points, then the Hessian, and so you already know the algorithm, but we'll do it together one more time. All right, so I put a condition that the partial derivatives of first order, they are all 0. Okay, that will be equivalent to the fact that 4y minus 4x power 3 equals to 0, and the other one, the derivative in function of y, that's 4x minus 4y power 3 equals to 0. Okay, the first idea that comes to our mind is to divide both equations by 4, and I get y equals to x power 3, and also I see that x equals to y power 3. Good. What can I do? Well, now, from the first equation, because y equals to x power 3, I replace, and that's x power 3, which is equivalent, if we look at the last relation, it's equivalent to x being equal to x power 9. Good. Or if I want, I can take x and bring it to the right, and we get immediately that x power 9 minus x equals to 0, which is equivalent to the fact that x times x power 8 minus 1, that's 0. So from here it implies the fact that x equals to 0, or the parenthesis equals to 0. So x power 8 will be 1. But if x equals to 0, immediately I get y 0. So the first point I got is the point of coordinate 0, 0. And from x power 8 equals to 1, I get x be how much?
We have m for yes, so y is 0 and x is plus minus 1.
Good, yeah, that's true. So immediately I get other 2 points. So what we remark is that x and y, they have the same sign. So yeah, we have to be careful to that. Yeah, why? Because y equals to x power 3. So if x is negative, surely y is negative. And if x is positive, surely y is also positive. Okay, so these are the points. Till now, I got the stationary points. Good, we have to go to the next step. Yeah, to the next stage of the algorithm. Now is the moment. I have to write the Hessian, if you remember. Let's write it in general. It will be it's that it's formed by the derivatives of second order of f. So I have the derivatives of f of second order in function of x, then in function of x and y. Here, the derivative of second order in function of y and x, and the last position it's occupied by the derivative in function of y. Okay, I replace by the values of the derivative, but I think I will move a little bit the page because we need to have in front of our eyes the derivatives of first order and then replace correctly in the Hessian. Okay, the derivative of second order in function of x, it will be how much? If you look, it will be
minus 12x squared.
good. Thank you. Also, I can put here on the main diagonal, it's minus 12y squared. I finished with these two. And now, derivative in function of x and y, it's
4 and 4.
And you know that's symmetric, so yeah. Okay, I will start to study for each point to see what happens. I prefer to study for M2, M3. You will see that I believe 0, 0 a little bit for later. Okay, so I will take the Hessian for M2. 1, 1. What I will get here? It will be minus 12, 4, 4 and minus 12. Good. Well, the first idea is to take the determinants. Why? Because it's easier. As I said, it's up to you. You aren't forced to use the same method as I. So I prefer the method with delta because I consider it faster, yeah? So look in our case, delta 1 is minus 12, and delta 2, you know, that's for a matrix with 2 rows and 2 columns, immediately that delta 2 is the determinant. So it will be 12 power to minus 16. Well, this is 144 minus 16, which is 100. How much it will be?
28.
28, which is positive. Delta 1, you see that it's negative. And by the Sylvester criterion, what follows immediately about M2? It will be a
maximum.
A maximum, exactly. It's but I have to clean a little bit. I don't like the way I wrote. So it's a maximum point, indeed. Yeah, I gave you the result. Immediately I get it's a maximum point. Yeah. Good. In the same way, faster, we study for M3. Okay, is the Hessian in minus 1, 1. I also get minus 12, 4, 4 minus 12. Yeah, so delta 1, it's minus 12. Delta 2, I can write directly, it's 128. So delta 1 is negative. The other one is positive, so by the Sylvester theorem, we get immediately the fact that M3 is a minimum. Sorry, is a maximum point. Okay. Maximum local point, of course. Local point. Okay, and I finished with those two. Now, I will take the last one, M1, and see what happens. When I take M1, immediately I get the matrix 0, 4, 4, 0. Yeah. Delta 1, I see that 0, so I can't apply the theorem with the determinants. If you are curious, But I think in this case, unfortunately, it works I think in this case it works the method with the eigenvalues, isn't it?
Yes,
Because
it works because it's
ah.
lambda square minus 60.
Okay. Okay, yeah, and immediately what we get? Lambda squared minus 16, it means that lambda one is 4, the other one, so nah, okay. Not exactly what I want. Okay. I wanted to get an eigenvalue different. Sorry, I wanted to get an eigenvalue, at least one eigenvalue be 0, but I don't
Let's
know
say we
why.
can put minus 4 here and we'll have lambda square plus
No,
60.
but we can't do that because, yeah, we have to use the information from our exercise. Okay, I will use the method with the eigenvalues, but you will see what I will do. Okay, unfortunately, I can't. Okay, I don't know why I had the impression that this exercise it's okay, but it's okay. Yeah, the method with the eigenvalues it works. Unfortunately, well, for you if you are at the exam, it's not unfortunately, it's very good. But for me, because I wanted to obtain something else, it's not so pleasant. Okay, let's denote this by something by A, and I take the determinant, it will be minus lambda 4 lambda squared minus 16 equals to 0. So lambda, well, I can put like this to be more clear. So one lambda is 4, the other one is minus 4, different signs. So unfortunately, the point is not unfortunately, well, that's not so bad for us. It's actually good because we are able to write the answer. So is not an extremum. An extremum. Okay, I wasn't lucky, unfortunately, but nevertheless, I will tell you what can be done if it's not working this method. So yeah, just a little bit, and then if this method wouldn't have worked, the idea, so what, let's say the problem is in some point, I don't know, f of x0, y0. Yeah. Let's say x0, y0, for this point, it doesn't work, nor the method with the determinants, nor the one with the eigenvalues. Okay. The idea is to find the Taylor polynomial such that, if you remember, I hope you remember the Taylor polynomial of first order and of second order. Is to find a Taylor polynomial. I don't know of what order. Maybe of order 2 it will work, but that's not a rule. Well, I promise that I will work and try to find another exercise till next time. And if I will be lucky, I will find an exercise where indeed those two methods they don't work. But as I said, what's the idea? We take a Taylor polynomial. If I take the difference between fx and f of x0, y0, I will get immediately. For instance, I want to use, I don't know, the Taylor polynomial of second order. Let's say that it's working. So here, when I do this, it will be the derivative in function of x computed at x0, y0 times x minus x0 plus the derivative in function of y computed at x0, y0 times y minus y0 plus. I said that I want to use a Taylor polynomial of second order, but as I said, it's not a rule. I saw exercises where it was necessary to take a Taylor polynomial of third degree, for instance. Yeah. Okay. Just a second to finish here, to write the formula, and then I explain you what's all about. What can be obtained in this way. So I apply the Taylor polynomial, and I know that I can approximate f of x and y minus f of x0, y0 by this expression. I write the Taylor polynomial of second order. And you will see at what will be useful. Okay, I almost finished, and then you will receive the explanations. Okay, so what's all about? Now, I repeat, let's say we are in the situation that x0, y0, it's a stationary point, and unfortunately, nor the method with the determinants, nor the one with the eigenvalues doesn't work. As I said, the idea is to use a Taylor polynomial. I don't know of which order we have to try to see which the order is best. So why I use a Taylor polynomial first? Because you know the formula of a Taylor polynomial of first degree, of second degree, and you know that it's a useful tool to approximate the function. Moreover, why we use the Taylor polynomial for local extrema? Because let's think, if for instance x0, y0, it's a point of minimum, let's say, then the difference between f of x and y and f of x0, y0, how should be? What kind of values should have all the time for a specific ball around x0, y0? What kind of values must have all the time? If this point, for instance, it's a minimum point, all this should have only positive, negative, or
negative.
Positive. If it's a minimum point.
Okay. Okay.
If it's a maximum, it will have only negative values. But if when I compute all this Taylor polynomial, I get an expression that doesn't keep the sign. What does it mean? That sometimes has positive values, sometimes has negative values. So can be x0, y0 still an extremum point if it doesn't keep the sign? The expression for all, what do you think? Well, no, because if it's an extremum point, or it has only positive values, or it has only negative values. Yeah, if I get something that doesn't keep this sign, which means that sometimes has positive values, sometimes has negative values, well, the conclusion is that is not an extremum point. So in this way, if you don't, if you are in the situation that you can't apply the method with the determinants or the one with the eigenvalues, you can use the Taylor polynomial to study what happens with your point. Is it clear? And
yes.
as I said, I promise that till next time I will be more careful and I will come with an exercise where indeed those methods, they don't work. Yeah, to see an exercise solved till the end where indeed we have to do something to determine what happens with that point. Okay, and that's it with this exercise. Sorry for not bringing for not bringing to you an exercise as I promised, but we'll solve that. Yeah. We'll do it. The next time I will be more. Now I will solve one more exercise of local extrema. Yeah, where we take a function and I want to determine its local extrema. Okay. And then we go to conditional extrema, because I said that today we will do only this kind of, we'll discuss only those things. By the way, at the seminar, more exercises with conditional extrema, something regarding the Taylor polynomial, and I don't know, probably if you have requests regarding of, I don't know, if you want to work more with you at the seminar, I mean, at the seminar we'll have on Friday, yeah, at school, let me know and I will bring to you more exercises. Okay. Let's go. And as I said, one more exercise. Also of local extrema. So let's determine the local extrema of the function, and because I want to have more space, I want to write here f of x and y, it will be 1 plus the exponential power y times cosinus of x minus y times e power y. Okay, that's it. But just a second. I'm not sure I wrote well the exercise. Just a second to check if it's okay written, because otherwise we won't obtain anything. Just a second. Sorry, I have to check if I wrote well the exercise, where it was. I'll find it immediately. It's important to write it well, because otherwise you won't obtain. Yeah. I found it, yeah, and it wasn't. My intuition told me, okay, that's something, it's odd, and actually it is, because the function, it wasn't written okay. So it's like this. It's 1 plus e power y times cosinus of x minus y times the exponent. Good. Okay, that's the function. Now let's work with it. Okay, what we do? Well, what we are used to do. Yeah, what we will learn to do actually, to put the condition that the partial derivatives of first order, they are 0. And let's see what we get. Well, I start to derive. Oh, when I compute d1 in x, yeah, how much I get? I will get minus sinus of x times 1 plus e power y equals to 0. Is it okay?
Yes.
Yes.
Now, the derivative in function of y, that will be 1 plus e power y. Yeah. Cosinus of x, I leave it the same. But here, when I derive, it will be minus e power y. Okay, minus what we get here, it will be y times e power y. And everything becomes 0. I hope I didn't miss something. All right. But I made a mistake, isn't it? Why? Where is the mistake? And it's here because this parenthesis, when we derive it, it doesn't appear 1. Yeah, I was in a hurry, and it's just so look, because I want to be sure that the computations are okay. So I derive 1 plus e power y. That's only power y, isn't it?
Yes.
Follow also the computations, because there are a lot of computations and we have to follow them together. Okay, let's write one more time. So I got actually minus sinus of x times 1 plus e power y. That's the first. Of course, everything equals to 0. And the other one, the second equation, if you see, we can put e power y as the common factor. So it will be e power y times cosinus minus 1 minus y, everything equals to 0. Okay, now we have to solve this system, but maybe it's better to take the first equation. From the first equation, it's 1 plus e power y, you know that's always...
I have a question.
Sorry?
I have a question. In
Yeah,
the
please.
last parenthesis, isn't it minus 1 plus y? Because don't we transform the...
The second equation, you mean?
Yes. Isn't it
Okay.
minus e to the power I plus y e to the power I from deriving?
So over here, you mean?
Yes.
Let's check one more time. If it's something odd and wrong, we will correct it immediately. So it's cosinus of x times...
I noted wrong. It's correct, actually. I
right.
noted
Okay.
plus instead of minus. My bad.
It's thank you. Anytime you see something which is not okay, let me know. Good. Now let's come back to our system. 1 plus e power y surely is different from 0, isn't it? It's greater than 1 and so on. So
Yes.
it can't be 0. The only possibility is that sinus be 0, isn't it?
Yes.
Okay, but maybe it's better to write it here one more time. So sinus is 0. But what do you know from trigonometry? When a sinus of x is 0, what's the solution of this trigonometric equation?
If I remember, it's 0 and pi over 2.
Pi over 2 is not a sinus of pi over 2. Yeah, actually, it's an infinity of solutions. That's the odd part of this exercise. It has an infinity of stationary points. Why? Isn't of the form k times pi with k integer? What do you think? Do you agree?
Yes.
Yeah. So x, it's of the form k times pi. So till now, an infinity of values, isn't it? Okay, I haven't finished with the stationary points because I need to get y. But now I will use the second equation. And from the second equation, the only possibility that this product be 0 is that the parenthesis is 0. Because the exponential, you know, that's a function that has only values different, positive, different from 0. Okay, now, if x is of the form k pi, so it means that cosinus of k pi, okay, minus 1 minus y equals to 0. So y will be, sorry, it's cosinus of k pi minus 1. But who knows how much is cosinus of k pi when k is integer.
The 1 or minus 1.
Exactly. So are you agree to write as -1 power k, the value of cosinus?
Yes.
Let's think. When k is 0, for instance, cosinus of 0, you know that it's 1. Cosinus of pi, it's -1. Cosinus of 2 pi, it's 1. So we remark that actually cosinus of k pi, it's -1 power k. Yeah. Sorry. So why it has this form? So I will denote in this way the points, the stationary points, they are of the form k pi and -1 power k minus. And I will, so an infinity of stationary points. Interesting, isn't it? Okay. Now what I will do next? I will start and compute the Hessian, but first I need the partial derivatives of second order. Because I don't want to make mistakes, I prefer to start and compute them here and then replace in the Hessian. The derivative of second order in function of x, look where it is. It's here, yeah? Let's take and derive one more time in function of x this relation, and we get minus cosinus of x times 1 plus the exponential. Is it okay?
Yes.
Here is the product, by the way, yeah? Cosinus times. Okay, what can we do next? The derivative in function of x and y. For that, what can I do? I can go here, that's the derivative in function of y, but I want to derive it one more time in function of what? In function of x. So I will get e power y times the derivative of the parenthesis, but in function of who? Of x. I get only minus sinus of x. Isn't it?
Yes.
Yeah, check the computations. Okay, and the last, the derivative in function of y, well, let's see here. It can be a little bit longer. I hope it won't be too difficult. The computations won't be too difficult. What I come here, well, here, yeah, and that we have to derive it one more time in function of y. Okay, we do it as a product of functions. So e power y derived, it's also e power y times cosinus of x minus 1 minus y plus e power y times the derivative of the parenthesis. How much is the derivative of the parenthesis in function of y?
It's actually -1.
Exactly. So I will put the common factor e power y, and I get immediately e power y times cosinus of x minus 1 is -2 minus y. Yeah, and that's it. And now is the moment to write the Hessian. I will write the Hessian. Okay. It's minus cosinus of x times 1 plus e power y. Here I have e power y times minus sinus of x. Also the same over here, it's e power y times sinus of x. And the last, it's e power y times cosinus of x minus 2 minus y. Okay, now let's see what happens in our points. We compute the Hessian in MK. And see what we get. Right. in MK, I said. Okay. But by the way, maybe it's useful to look at something. And don't forget that for MK, for the points MK, sinus, it was 0 in XK. And also we have what? We also have something, cosinus of X, it's 1 plus Y. It's important to have in mind those things, yeah, because it will be easier for us to make the computation. So look that cosinus of SK, of XK, it's 1 plus YK, yeah? It's easier for us. Okay, so let's come back here. It will be cosinus of K pi times 1 plus E power, how much it was Y? If you have in front of your eyes, please tell me, it's easy for me. I think it was minus 1 power K minus 1. Yeah, it's okay?
Yes, that was.
Okay, I put like this. Sinus of xk is 0, so here it's 0. And here it will be a power yk. That's minus 1 power k minus 1. I write the value of yk times cosinus of k pi minus 2 minus y. Minus y, it's minus 1 power k plus 1. Okay, and that's the Hessian. I have to work a little bit more because it's not enough here. Good. So minus cosinus of k pi, I know that's minus 1 k. Here I leave as 1 plus e power minus 1 power k minus 1. Here it's 0. Also here it's 0. Here, let's say what we get. It's e power minus 1 power k minus 1 times minus 1 power k minus 2. But minus 2 plus 1, it's only minus 1. Minus k. Okay. Also, I can reduce by something, I see. What? This and this goes away. Probably it will be a discussion in function of k. It is possible. 0, 0, I will put here. So what remains? On the position 2, 2, it remains only minus the exponential power minus 1 power k minus 1. And here becomes minus 1 power k plus 1. And what else we have? Okay, plus minus 1 power k plus 1 times the exponential power minus 1 power k minus 1. And that's it. Okay, what I'm thinking to do is to try to use the method with the determinants, isn't it? Moreover, surely the determinants, they will be 0. Why? For instance, look at delta 1. Let's take delta 1, for instance. Delta 1, if I put the common factor minus 1 power k plus 1, I get 1 plus the exponential power minus 1 power k minus 1. Yeah, that's it. Which this parenthesis is not so important because surely it has only positive values, isn't it?
Yes.
But it will be discussion in function of k plus 1 actually. And I will put like this. It will be positive, strictly positive when k is odd, isn't it?
Yes.
Of the form 2k plus 1, and strictly negative when k is even. All right, good. Now let's see how much is delta 2. You know, it's simple. It will be the determinant of the matrix. It can be, by the way, the delta 1 can be 0?
No.
No. Yeah, there isn't such a positive, so it's okay for us. Good. Delta 2 will be the product actually between, so it will be minus 1 power k plus 1 times 1 plus the exponential power and so on, times minus 1 times the exponential. Well, but you see, the exponential doesn't influence the result, isn't it? Because it's positive, 1 plus the exponential also is positive, so they appear in the expression all for delta 2, but it doesn't influence the sign. So I get actually minus 1 power k plus 2 times the exponential power minus 1 power k minus 1 times 1 plus e power minus 1 power k minus 1. Yeah, and now let's see what we get. Here it will be a little bit different from delta 1, isn't it? It will be exactly the opposite. So what happens when k is odd? It's
Negative.
And when k is odd, it's even, is positive. All right, so let's write the conclusion then. So after all this long discussion, the exercise, it was a little bit long, but I don't think it was so difficult. By the way, questions till now? Something unclear or remarks?
I think it's clear.
No, okay. So what we can conclude? For so when k it's for instance even, we get that. So let's look very well. What happens? Delta 1 it's negative, delta 2 is positive. So m in this situation, mk, what kind of point will be?
Maximum point.
Maximum, yeah. So mk is a local maximum point. Good. For when k it's odd, the situation changes. For k odd, we get delta 1 negative, delta 2. Sorry, it's the opposite, isn't it? Delta 1, sorry. Delta 1 it's positive, strictly positive, of course. And delta 2 is
Negative.
negative. But from the Sylvester theorem, what we know in this situation?
It's not a local extreme point.
Is not a local extremum point. And that's it. Other situations we don't have, isn't it? And we finished. So the conclusion is that an infinity of points are local maximum points also there are an infinity of points which aren't local extremum points. Also, we remark that we don't have any minimum local points. Yeah, interesting exercise. But this is an exercise where we see that there are an infinity of local extrema points. That was the aim of the exercise, to show you something new. That's what we work at the seminar. Yeah, at the seminar we had a finite number of stationary points and we worked with them. But we see that there are functions such that they have an infinity of local extrema. Okay, questions till now? If not, then let's go and solve some exercises of conditional extrema. So that's what we will do in the following moments. Okay. Also at the seminar, I promised you that I will come this evening with examples such that there are, we worked at the seminar, if you remember, only with exercises that had only one condition, yeah? And we had only one Lagrange multiplier. But I promise you that today I will come with examples where we have several conditions. So we'll have several Lagrange multipliers. And such is the case of the following exercise. It's a conditional extrema. It's an exercise of conditional extrema. The request, it is to find the conditional extrema. The conditional extrema of the function f of x and f. It will be a function with three variables. It's x times y plus y times c plus x times c. So that's the function with the conditions. We have several conditions, well, two conditions. These are minus x plus y plus z equals to 1, and also x minus z be 0. Okay. These are the conditions. This is the exercise. Good. So, solution. Now, because I have two conditions, how many Lagrange multipliers do you think I will have here?
2.
Exactly, we have two. Okay, that's it. So, we construct that function f with capital, but it will be in 3 variables this time. So also it's something new from what we work at this seminar. I remember that I work only for functions in 2 variables. Sorry. It's f of x, y, and z plus lambda 1. But how I will write here the first condition? I leave it like this or I will make a change? I put minus x plus y plus z minus 1, yeah, such that be 0, the parenthesis. Yeah, remember what I told you at the seminar?
Yes.
No, okay. Plus lambda 2 times x minus z. Okay. That's f. What I did? Sorry. I don't know what's going on. Okay. Now, I don't know why the page is moving. I don't like this.
I have a question. Since
Please.
x is equal to z, can't we make only one condition from this?
Yeah, but yeah, it's not a bad idea. We may go and replace. Yeah, this kind of exercises can be solved in different ways. It's not the only way to take like this as I did. Yeah, x it's z, so I can come to the first condition and we get what only y equals to 1, I think. Yeah. So
Yes.
this help us. Yeah, it's a good remark. Yeah, it's a positive to do it like this indeed. One of the positives is to take with 2 Lagrange multipliers. So do it as you want. Yeah, but very well, good remark. But I haven't remarked the name of the student who came with the idea.
That's me, Kinsoy.
Okay, Vladut, very well. Yeah, good. From which group are you?
1211A.
Good. Okay, I will do it. If I started with the Lagrange multipliers, I will do it like this because what I want is to show you there is a positive to do it like this. Okay, so we do it as we talked at the seminar. We take the derivatives of first order, but of the new function. Yeah, we put the condition that those are 0, and we add also the conditions. Okay, if you do it like this, I put minus x plus y plus z equals to 1 and ex minus z be 0. Okay, I will need some help because I don't want to make mistakes. Please follow me. F deriving function of x, how much will be? It will be y, isn't it, plus z minus lambda 1 plus lambda 2 equals to 0. Is it okay? Please check the computations.
Yes, it's good.
Now, f deriving function of y, it will be x plus z plus only lambda 1 equals to 0. Okay. The third one, f deriving function of z. Well, this is probably x plus y plus lambda 1 minus lambda 2, everything equals to 0. Now, I add also the conditions. And this is it. Okay. From the last, I get x equals to z. Moreover, we get what? If x equals to z, y will be 1. Okay, that helps us a lot. Now, we need to determine who x and z they are. What we can do, well, if y is 1, from the third one, I get x plus 1 is lambda 2 minus lambda 1, one idea. What we get also, you know, another idea is to, if I will add the first and the second, what I will get. Lambda 1 disappears. X, I know that's how much it's equals to z. Y, it's 1, so I get from those two. I think it's 3x, isn't it? Plus 1 plus lambda 2, everything equals to 0. Is it okay? Please check. Yeah, it's good.
Yeah, it's okay.
Yeah, we need to determine so I have this equation. Also from the second one, I know that lambda 1 equals to minus 2x. Okay. So lambda 1 can be written in function of x. Lambda 2, well, should be written... I want to replace everything. Yeah, we stay too much at this system. So I know lambda 1 is in function of x. So lambda 2 it's so
It's
I
also
have
a function of x.
Yeah, lambda 2 it's also in function of x. Yeah, well, just a second. So lambda 2 it's also in function of x, and how much it is? So it's minus 3x minus 1. Okay. If I go here, so x plus 1, x plus 1, I know that's lambda 2 minus lambda 1. Okay, at what help me this? So x plus 1, lambda 2, I put minus 3x minus 1, minus lambda 1, but lambda 1 it's minus 2x. Okay, so it will be minus it's plus, if I compute it well, but I want to check. Yeah, it's lambda 2 minus lambda 1. It's good. So from here, what I get, it will be equivalent to the fact that x plus 1 equals to minus x minus 1, if I see well. So 2x equals to minus 2, so x is minus 1. Okay, I got x minus 1. It follows immediately that z equals to minus 1, and y I already know that's 1. Okay, I want to check a little bit the computations, because we have to be sure that we solved well. So x is minus 1. Let's replace, for instance, here. Let's see if it verifies. Minus x, it's 1. 1 minus, it's good. Another part. So I see. I hope it's okay. What do you think? You follow the computations? I got the point minus 1 minus 1. Did you follow the computations? They are okay?
Yes, I think they are okay because I get the same result.
Good.
Yeah, they're okay.
Thank you. All right, so only 1 point, good. Now I go further, and I have to take the differential, but the differential of second order of f. Okay, we have to remember the formula. It's first be easier for us to keep in mind the formula. Here it's dx squared. The derivative now of f in function of y, dy squared, plus the derivative of f in function of z dz squared. And I have to continue with the mixed derivatives, but of f with capital in function of x and y. Here it's dx dy and other two terms, and we finish this part. Here is the derivative of f in function of y and z dy dz, plus the last term is the derivative, it's 2 plus the derivative of second order of f in function of z and x, dz dx. Okay, and we have now to replace carefully. F derived in function of x 2 times, how much it is in function of x only? It's 0, isn't it?
Yeah, it is 0.
Also, because it's difficult for me to move the page upside down. Also, we remarked that the derivative of second order in function of y is 0. Also, we remarked that the derivative in function of z of second order, they are also 0. So the first terms, they are all 0. Yeah?
Yes.
Okay. Now, let's see the mixed derivatives. F derived in function of x and y. I will have to move the page. Okay. So in function of how much I said, x and y. So I take the derivative in function of y, but I have to derive it one more time in function of x.
So it's 1.
It's 1. Yeah, it's 1. Okay. Maybe if you please help me a little bit. So that's 1. I get dx dy. Who can tell me with the derivative in function of y and z? It's difficult to move the page. So the one in function of y and
It's
z,
also 1.
it's also 1.
And the last one is also 1.
Yeah. Okay, that's the interesting part. If you look at this expression, it's a quadratic form, but unfortunately it's not at the canonic form, isn't it? If it has dx squared,
Yes.
dy, yeah. Okay. Of course, we may take it if we want and bring it to the canonical form as you learn at linear algebra, but it's too difficult and there is no need here at calculus. Why? Because don't forget that I am interested only in studying at the point M, but at the point Y, M, Y is 1, so dy how much will be immediately? When I differentiate Y, it's
X. Y. Sorry.
Oh.
No.
dy becomes?
Oh, it's 0.
Yeah. So all the terms where appears dy, they disappear. Okay, so till now it's only 2 times dz dx, but also I see another thing. X equals to z, if I remember well, isn't it?
Yes.
So dx equals to dz. Is it true?
So it's actually 2dz squared.
Exactly. So, or I can write 2dx squared. It's the same, yeah. Which is obviously a positively defined quadratic form, which means that my point is a minimum or maximum conditional extrema.
Minimum.
Yeah, it's a minimum. Good. A minimum conditional extremum point. And we finished. And that's it. Yeah. So sometimes the exercise we did at school, it was a little bit easier. From the computations of the partial derivatives, we got, I think, if I remember well, we got the positively defined quadratic form, isn't it? And it was easy.
Yeah.
But here, at this exercise, we had to work a little bit more to get the quadratic form to its canonical form, but you saw it wasn't too difficult. Yeah. Okay, and that's it. Because it's a little bit too late, it's 14 past 10, I will stop here. I will continue at school with conditional extrema, and of course, next time, by the way, next Tuesday evening, but I don't know the hour we'll talk at the seminar, but just to have an idea, next Tuesday, is it okay for you, for everybody?
I think so, since we're in the session.
Yes, I think so.
Yeah, we are in, yeah. But next time I will have a revision, yeah. Because we need to prepare for the exam and it will be a revision. The exercises will, well, it won't be the same level. It will be a little bit easier because we prepare for the exam, for the final exam. So we'll work exercises like similar to those you will receive at the exam. Yeah, so it will be only a revision. But I want to know if it's okay for everybody to have the meeting next Tuesday.
Yes, it's okay.
Okay. I hope you don't have an exam next year on Wednesday.
For our group, we have only on Monday. Thursday is 23, no? If I calculate correctly.
Yeah, it's 23. Yeah.
Yes, on 22 we have an exam. Our group.
Good. Maybe you are tired and you don't want to have, I don't know, a calculus lesson in the evening. So that's why I prefer to meet with you on Tuesday to be, I don't know.
Yeah,
For our
Tuesday
group
first.
12 level A, it's good because we have the calculus exam on 26. So it's good.
Okay, good. Yeah, so your group, it has on 26. There is so which are the dates? You on 26, the others, when do you have the exam?
30,
30?
31 January.
31 of January. Okay, 31, 24.
C has on 25th.
25th. Good. So I think on Tuesday is perfect for everybody, I think.
Yeah.
Yes, it's good.
Perfect.
Yeah, it's good.
So,
Well, all of us have the same exam on Monday on the 22nd, and it's impossible for anyone to have anything on 23rd and 24th because the rule of the faculty is that we need to have 3 days between the exams, so we are safe.
Good. Good. So, I think it's okay to meet on next Tuesday. As I said, the hour, we'll establish it at the seminar. We'll talk together and see which is the best option for us. Okay, thank you for your attention.
I wanted to ask you.
Yes,
Did
Antonio.
you post the assignment on Moodle, because I cannot find it?
Oh, sorry, and thank you, Antonio, for reminding me. I will do it immediately. Yeah, sorry. Yeah, I know. I promised you to. Yeah, I gave you an assignment, but I forgot to prepare it. Sorry, I have a lot of things on my head, a lot of things.
No worries.
Yes.
No worries. It's
Yeah,
okay.
is the last weeks for me, for everybody. For me and for my colleagues, is the same situation. We are so occupied, and yeah, thank you for reminding. I will do it immediately. Yeah, I will go on Moodle and prepare the assignment for you.
Okay, thank you very much.
Thank you too. Good. So thank you for attending this this meeting, and see you soon at the seminar. Goodbye.
Okay.
Have a nice
Goodbye.
evening.
Have a nice evening.
Good night.
Goodbye.
Bye.
Have a night night.
Thank you. Good night.